All right, we are very close to the punchline and to the conclusion of this subject. So you made it through in one piece, which is good. So a little bit of patience. So we are all tired a little bit, and therefore I'm limiting myself pretty much to just qualitative discussions now, because algebra at this stage it will just might be too much. So if you're ever seriously interested in the subject, you will obviously need to go through the papers. But my goal today is to give you an idea of what was done, what was wrong, and how to solve the rectify the problem, and more importantly, to understand what we get as a result of this. Okay, so that's basically what my goal is. And I'm doing a lot of qualitative discussion, qualitative things presented here. So, and hopefully it makes some sort of sense to you. As I said, so this is has been not well understood for 65 years, and therefore if you have any difficulties with understanding the algebraic details of what I'm doing, so that's normal. It's not like you are the only ones who are in this situation. So I myself, it took me quite a while to understand what is actually going on here. So, all right, let's continue just with a qualitative description of what we are trying to achieve now. So we have base flow, we have perturbations which are imposed on that base flow, and those perturbations develop in supercritical regimes, so we are not linked to a bifurcation point in any way, and we don't want to be related to or somehow chained to bifurcation point. So what we have linear stability problem where, which can be solved, and we have solved it at arbitrary value of governing parameters such as Reynolds number. And this is not necessarily Reynolds number critical. It is just arbitrary Reynolds number. And we have W11, which is eigenfunction computed by solving linearized problem at this particular Reynolds number. It is not a critical one. It's just some Reynolds number. So what you will get by executing any numerical code, you will get some sort of eigenfunction given numerically. And black box routines such as MATLAB will produce some sort of numerical output that is scaled somehow, and you don't know how. MATLAB will do it itself and just spits out the set of numbers. Do you care about that? The answer is no, right? If you need to somehow change that eigenfunction, well, just take that eigenfunction and multiply the whole thing by 2 and nothing will change. Or divide it by 2 and nothing will, as long as you do not divide or multiply by 0, everything goes. Okay, so we don't care. So take this eigenfunction and as is, and don't do anything like that, and I will draw it like that. So this is what the MATLAB spits out. And we know that that will be eventually, or we will plan to multiply that output by some amplitude, which we don't know at this stage. Okay? So that's basically where we are. And then we proceed and we will solve the problem at this level. Say, well, I assume that we actually solve that problem. So there are problems where there are difficulties with that. There is that issue of k. But let's say we solve it. Let's say that we solved it. And we get another vector. MATLAB spits out this vector and it looks like that. Okay? So that's what we have. That's what we have in practice. Neither this nor this are known. But of course, these are not arbitrary. They are related to each other. If you know that, then you know that. Okay? So that's what we have. What do we want to achieve? This is the solution that we would like to achieve, right? And the way we would like to achieve, to get this solution is by simply taking these components and adding them together so that we'll get that. So that's what we have. So we have these, we don't have their lengths. So we have directions, but we don't have lengths. Okay? So, therefore, how can we do that? So, well, if I want to get this, I will take this as is, for example. Right? And then I will take this and try to add it. So that I'm taking this and drawing it like that. And then I take this and draw it like that. That's basically what MATLAB gave me. And I simply add them together. And you can see I didn't get where I want to. I get somewhere, but not there. So what do I geometrically need to do to get where I am? To get to this point. What would I need to do? So I have this, I have this. What will I need to do? No, geometrically. So what will I need to do? So this is one vector, this is the other vector. Well, I took them as they appear from MATLAB. So I would need to stretch it. Stretch, right? So I see that it has just undershoots. So I need to stretch it. So therefore, instead of having that, I would need to simply make this as a little bit longer and this a little bit longer, and then I will get where I want. Agree? So that's what the meaning of this A is. It's a stretching parameter. So if I do not have A, or if I set A equals to 1, as I did when I plotted all these fields, I will simply do not get where I want to be. But I can potentially by simply taking that A and stretching this. So if I stretch this, and then I will correspondingly stretch this, so I will have a better chance of getting where I am. Agree? So, okay. So that's the basic idea. So A is there as a stretching parameter which I can adjust somehow to get where I want. So can I really always get where I want? Well, unfortunately not, because if, for example, well, in this case I drew it like that, but if I had the vector which would be like that, right, and I have this and I have that, so no matter how I try, no matter how I stretch, I will not get there, right? So I will be able to cover vectors along this line, but not along this line. You see that? So we will never get exact match. But what we will try to do to get as close as possible. Right? So in this situation, probably that would be a sort of a best thing we can do, because if I stretch it, overstretch it, then I will be further away from where I am. Okay, so is that clear? So the point is that we cannot really always guarantee that we will recover this whole thing, but by playing with the amplitude, by stretching this, we might be able to minimize the error. We might be able to try to get as close as possible. Is that clear? Okay. Now, there is one more trick here, which is quite important. And that's, well, I take the credit for that. Well, this is not the optimal way of doing that. The optimal way of doing the same thing would be if this is my W11 and this is my W31. Not like that, but if they are like that and like that, just think about it. So what's the difference between this and this? Geometrical difference. Angle. And what exactly angle? That's a right angle. And why do I say that this is optimal? In what sense is it optimal?
Yes.
We don't know anything about stretching, but rather about what sort of information is contained in each of these vectors. So if the situation is like that, so W31 is semi-parallel to the original vector. So therefore, it contains the same information as this one, plus something else, but also some sort of which is in the direction of W11. So therefore, adding these two together is simply equivalent to taking this and stretching it a little bit. You see what I mean? So mathematically that means, so you have some component. So this is the component that you would like to recover. That's horizontal component of the full solution that you would like to recover. And what we are doing that, we're sort of doing that, but we are taking this, and we initially, when we solved the linear problem, we added this bit. That's what happened when we solved the linear problem first. And then we solved the second problem, so cubic problem. And then we add a little bit more. Really, that's what happens. And then if you go to the next level, so if you compute, for example, a to the power of 5, or 4, something like that, so higher orders, we can continue, of course, that. Then we will add a little bit more. So every time we expand something, we effectively modify what we already had. Is that clear? So, and that means that if I stop at some point, for example, I don't want to go beyond that, so I got tired of that. But my procedure tells me that every time I do something, I change what I have. Every time I do something, I change what I have. That logically means that what I have is incomplete. Agree? So if every time I add something, I change what I have, it means that what I have is incomplete, it is changeable. So therefore, by stopping this addition process, I consciously say, well, yes, I admit that I have an error in my representation. Is that clear? Because I know that if I if I keep adding, I will be changing, and I stop adding, which means I stop changing, so therefore I am satisfied with the incorrect result. Knowingly incorrect result. Is that clear logically? Okay, good. What will happen if I have two vectors like that? So I have my W11, and if I add W31, I will add it like that. So whatever I had is not changing. And if I add something else, I will add it here in the third direction. And I will not change that either. So every time I have something, if I decide to go to the next level, I know for sure that what I have will stay. It's not going to change anymore. So therefore, if I stop process, then I know for sure that what I have is final. It's not going to change anymore. It is absolutely correct. It might not be complete in that sense that there will be other components to it, to this vector, perpendicular components, but at least this one is not going to change. Is that clear? So therefore, coming back to here, so that means that if I have the situation like that, I need to stretch it only once and by a very definite quantity. So therefore, what I have is this W prime that I would like to have. So this is my W11, which comes out from the MATLAB. And obviously, it does not really match what I want, but what I have this A, stretching coefficient. And I choose my stretching coefficient once, only once, and I choose it in such a way that it stretches this W11 exactly where I want it. I don't want overstretch it or understretch it. So this is my one only stretching of W11. It occurs at very first term, and after that, if I add anything, after that I will be adding in this direction, but not in the same direction. Is that clear? Okay? So that's basically how it works. So if I need to stretch, I will stretch. So I will choose my amplitude in such a way that my vector, my eigenfunction, linear eigenfunction, will be rescaled, but only once. So MATLAB gives me something, I take that, and I multiply what I have by amplitude, and I get the right thing, and after that I keep it fixed. I do not change it anymore. Ever. No matter how many terms I add after that, they will be adding something completely different, but I will not be changing my linear eigenfunction, how it looks. Is that clear? That's the point. Okay? So that's what happens. So therefore, in order for this to work, I need to make sure that when I solve the problem in the first instance, so my W31 looks like that. Okay, so therefore, I need to make sure that when I solve the problem, and by that I mean I choose the value of that constant k, because constant k is required to solve this third order problem. I choose it in such a way that the solution that I will obtain will be like that. So that is the proper condition that I need to impose. Okay? So the condition which is natural for this problem is not that phony adjoint condition, which has to be applied somewhere in the galaxy far, far away from here. It is the local condition. Locally, I have this local eigenfunction computed at the local Reynolds number of interest. And all I want to do is to use it at its full, right? So I take it, I scale it once, and after that, I do not touch it anymore. So any further additions to my expansion will not modify what I already have in my expression. So that is the main thing which was not introduced prior to me. Okay, so that's basically the idea. So now the question is, once we understand what our goal is, how to implement this in practice, numerically. So obviously that's a good idea, so geometrically, qualitatively it might be clear, but how do we enforce this? So how do we actually, what equation do we specify to solve for this to be the case? All right, so now let me go back to my slides. Oops. To my slides. So let us look at what I have here. So what I have here is a modified operator. So remember, before we solved the problem, lambda, or sorry, L of alpha sigma plus 2 sigma r, 2 sigma r is equal to right-hand side F31 plus constants of whatever was there. So let me just have a look, see if yes, so that's the problem that we had before. Okay, except I have minus sign missing here. So it's written in a slightly different form, so it is k here rather than minus k. So that's what we had to solve, right? So what I do now, I reformulate this problem. In what way? I state that this is one of the unknowns. Okay, so right now it is in the right-hand side like if I know it. So I do know what F31 is, but in reality I still don't know what k is. It needs to be defined, right? So therefore I push this term to the left-hand side. Okay, so then my unknowns become W31 and K. They're both unknown. Is that clear? So if I push this to the left-hand side, then this is unknown vector. That's what we need to find, but this is also unknown. So in this sense, we will have a system of equations which contain one more constant, unknown constant, one more variable, right, in a sense, and we need to define it. Is that clear? So essentially we have n equations for W31 plus 1, and we have n unknown variables in W31, but we add another variable k. So now we have n equations sitting here and n plus 1 unknowns. So we can't really solve that. We have more unknowns, one more unknown than equations. So we need to invent the extra equation. Okay? So that's basically what we have to do algebraically. And we know what that equation should represent. It should represent the condition under which what we obtain, this solution W31, will be perpendicular to W11. W11 is already known. Is that clear? So that's all fits together. So now we have extra unknown and we have an extra condition, orthogonality condition. And we know why orthogonality is required. And that's what we will need to solve numerically. So my problem will become this. So essentially this comes from the fact that k is also unknown. So therefore if you take this multiplied by W31, that will be your original system of equations. But in addition to that, you will have plus k multiplied by b multiplied by W11. K is unknown, so therefore that will be extra column in this matrix. And we need extra equation for k. So, and that will be added in the last row in this modified matrix. So that's what we are doing. And in that case, we can invert this matrix, and we will go and we will obtain our solution and the value of k simultaneously in the same run. So therefore we will simply increase the size of the matrix by 1, invert that matrix, and get the solution. That is what the idea is. And the condition, additional condition, is orthogonality. So essentially what we get out of W31 is perpendicular to W11. Okay, so that's what we would like to get. So k is responsible for that extra condition. All right, all good. The only thing left here is to discuss what orthogonality actually means. So if we have two vectors, geometrical vectors, how do we define orthogonality? So what is the condition under which the two vectors will be perpendicular? So one vector contains coordinates, say, x and y. The other one is u and v. So how do we know that they're perpendicular to each other? Dot product, x times u plus y times v is equal to 0, right? So that's the condition. As simple as that. Now, what are our unknowns? Our unknowns are u, v, p, pressure, so u component, velocity component, v, velocity component, p, pressure, and now k. Agree? So what do we want to make orthogonal in a sense? So which components? We have u, v, p. K, of course, is not part of it. It's just an additional variable. So what do we orthogonalize? So what do you think? So what is the difference how the variables appear in the equations? So u, v, and p. What's the difference between how u and v appear in the equation and how p appears in the equation? So what is the main difference? If you remember the structure of the equations. What does u
and V, well, just forget about physical meaning
of them, just structurally, algebraically. We have equation for U, we have equation for V, we have equation for P. What do equations for U and V have, which equation for P doesn't? Sigma comes from where? Time derivative. So remember, momentum equations have du by dt, dv by dt. And continuity equation, which is formally is equation for pressure, does not have it, right? So the continuity equation doesn't even have P itself in it. So therefore, P plays a completely different role. So therefore, if we have U and V and another vector U and V, what's the dot product between the two? U squared plus V squared. And what is that physically?
U squared plus V squared. Now, U is actually the velocity component, right?
So U squared plus V squared. What does it give you physically?
It's kinetic energy. So, all of a sudden,
everything falls in place even physically. So we have the geometrical interpretation, but now we know what it means. So we would like to choose our solution in such a way that the kinetic energy, which is accumulated in the perturbations in the eigenmode, does not change when we add extra modes. So therefore, extra modes, extra solutions, extra terms, they will add the energy to perturbations, but they will not change the energy which is already there. That's what the physical, one of the physical conditions which we can impose here. So, but for this, we need to exclude pressure out of the dot product. So therefore, we want U multiplied by U plus V multiplied by V and nothing from pressure. That's what we want. So it is our choice. It's not a necessity. It's our choice. We would like to choose our dot product in such a way that it is physically meaningful. It represents kinetic energy. So, and this brings us to the next thing, subtle thing here. That's basically what we have here. It is in the first position, so therefore that, how does it work? It is this multiplied by that, so you see it is W11 multiplied by W31. So this is a dot product between two solution vectors, right? And we would like it to be 0. But we don't want to take pressure into account, right? Why? Because, well, we would like to deal with a physical quantity, which is kinetic energy. And including pressure would spoil that. So we would like to get rid of that. So therefore, we will need to stick this weight matrix in the middle. And in this case, in the case of kinetic energy, matrix M will have just this very simple form, 1, 1, and 0. So therefore, if you take a vector U, V, and P, and multiply it by this vector, what will you get? You will get U, V, 0. So pressure will disappear. And then you multiply it by another vector U, V, and P, and you will get U times V, or U times U, plus V times V, plus P multiplied by 0. So P is gone. So therefore, this is the matrix which we need to stick in if we would like to stick with equation with kinetic energy. So, and the result with that we will obtain after that will be that your first term in your expansion will contain the kinetic energy the way it is present in the physical system, and it will not be changed afterwards by algebraically adding extra terms. Is that clear? So that's the idea here. So basically this is, of course, you are free to choose any other metrics. For example, for whatever weird reason you would like to include pressure, well, go ahead. Just use this matrix, 1, 1, 1, identity matrix. Or for whatever reason you don't like to include V and P. So, well, in that case, you will get 1, 0, 0. So it is completely under your control. So This is another advantage. So now you are in complete control of what you would like to compare. You would like to look at kinetic energy? Go ahead. Set it like that. You would like to see what happens with the system as if it were like a proper three-dimensional system with three-component vector. Well, choose identity matrix. This becomes very important, especially if you are talking about problems where you have, say, some other influences. For example, many of you asked me about convection problems. In convection problems, you have another variable, temperature. And you have extra equation, thermal equation. So you have kinetic energy plus thermal energy. And in that case, it becomes non-trivial when you consider energy of the system. Do you simply consider kinetic energy? Do you simply consider thermal energy? Do you have to consider both? And if you consider both, how do you mix them together? Right? So you can, obviously you can take, they come from different sources and they might have different meanings. So what's the meaning of thermal energy and what's the meaning of kinetic energy? So you need to somehow add them together, and this problem arises frequently if you are dealing with so-called energy methods. I'm not going to go into that, but that's what happens. How do you mix those equations? You have momentum equations, you have thermal energy equations, so, and they produce their own things, but then you need to somehow add them together. So how? Well, up to you how, but this mechanism will allow you to do that. So basically what you will have to have in that case, 1.5 or 1 Prandtl number. See? So it is all your choice. All of a sudden it is your choice now. And you can use it to your advantage. And coming back to that post-shadow sun problem, what it means by changing this matrix M, which essentially specifies what quantities, what characteristics you would like to extract from your system, you're fully controlling the angle. So this is the post, this is the shadow, and this is the light source. And by choosing that matrix M, you're choosing the location of this light source. And by throwing the shadow under some different angle, you will see different features. The same system, the same method, everything the same, but you will be emphasizing, we're looking from different angles onto the same problem. And you will be extracting them one feature at a time, not like in direct numerical simulations. You will simply throw everything and let it boil and try to eat the soup. No, you will be able to see each individual ingredient separately, investigate it. Well, this is salt, this is peas, this is water, this is something else, curry, whatever you put in soups here, quite tasty, by the way. So all soups I tried in my dormitory, in my hostel. Anyway, so it is all at your will. You choose, you decide what you want to do, you decide what you look at, you extract the features of interest to you at this particular moment. Tomorrow you might extract something else, and this will not cost you much. You saw how quickly this runs. So, pretty much I'm finished with this, and the only thing I want to add is maybe to run the code once again, this linear stability code, and come on. So these slides are in the folder already, so let me just run this code, and so all these pictures I will not discuss them again. We did it yesterday. So all that, all that, all that, all that. So that's the animation. So let it run. So you see there's waves running. So I got stuck doing something. All right, so I'm not sure what it was doing. So it probably started updating or upgrading something. So that's why it was all, so stuck there for a while. But the output which appears on the screen, you cannot read it, it's too small there, but it says adjoint eigenvector. So actually what I've done, what I implemented here in this code, I used this adjoint operator mechanism, and it got stuck a little bit. And the reason why, because I formally need to solve the eigenvalue problem. So I solved the eigenvalue problem for direct formulation already, so plotted those sigma values, and then if I am to use this formalism, the deficient formalism, that brings me back to the bifurcation point, which we realized is completely unnecessary and harmful actually. Not only that, it actually asks us to spend more computational resources by resolving the same eigenvalue problem, but now with the transposed metrics, right? So you're actually wasting time. It's not only you are doing something which is not necessary, but you are wasting a lot of time on just computing. So computation of eigenvalues is not a cheap procedure computationally. So nevertheless, I did it there, and what you will see there is that eigenvalue, adjoint eigenvalue problem is solved. I found this W dagger thing, and now I'm in a position to define the Landau constant. And yeah, again, you cannot see it from where you are, but unless you run the code, and you will see that it actually evaluated the Landau constant, and it is printed out here. Now, one logical question you can ask me, challenge me on that is, all right, that's the good method you suggested, so orthogonality. But you're telling me that orthogonality can be your choice, right? So you can choose to look at the kinetic energy, or kinetic energy plus pressure, or kinetic energy plus thermal energy, right? It's your choice. But what happens if you go back? So you take your choices and you go back to critical point. And at critical point, when we looked at the critical point, so none of that works. You need to stick with the adjoint. You see the problem here, the logical problem here. So I'm telling you that if you are away from the bifurcation point, you have those beautiful choices. You can do that and that and that and enjoy life, right? So in all its diversity. But if somehow you decide to take these computations back to the critical point, will they break? Because at the bifurcation point, we know that we don't have any choice. The solvability using a joint operator is the only way to go. There's no other way to go, because there, amplitude is essentially zero. The problem is linear, effectively linear, and therefore linear solution is only one. It's when you have a nonlinear solution, you have all these options, multiple solutions. But if it is linear problem, and it is linear if amplitude is equal to zero, then you have a single solution. And that solution can only be obtained by using the formalism, adjoint formalism. It's just algebraic fact. So logical contradiction. Here you have choice, here you don't have, and you move from one to another in a continuous way. You just do not jump there, right? You continuously approach a point, and every time you are slightly off it, you have those beautiful choices, have your beautiful choices, have your beautiful choices, don't have any choices. See? Again, this is a problem because that's a contradiction. So you do something continuously and all of a sudden you jump from having choices to not having choices. You had them and all of a sudden you don't. So discontinuity. Logical discontinuity, right? So, last note I will say is that it took us quite a while to actually show formally that when you take all these choices and when you bring them continuously to a bifurcation point, then no matter what you chose, they will all automatically collapse to this formalism, adjoint formalism. You don't have to worry about that. No matter what you choose, follow it through all the way to the bifurcation point, and the result, by the result I mean this Landau constant, the value, numerical value of Landau constant, will be the same no matter whether you choose kinetic energy, whether you choose thermal energy, whether you choose whatever you chose. You come back to that point, and all the methods you tried, you choose, will give you exactly the same value of Landau constant as adjoint formalism. So therefore, adjoint formalism is a limiting case of these orthogonality approaches. You don't have to worry about the choices because any of those choices will work. They will show you different features, but it's like if you have a post and the sun shines on this post from this angle, from this angle, from this angle, you will see different shadows. So it is your choice. Now sun starts rising and it is here. So it is continuously rising. And all these various shadows, they collapse to a point. Not much information there, but no matter where you're coming from, you will collapse to the same point. Not much information, but the point is that you do not converge somewhere else. You converge here to that single point. So that is really what the achievement is. And it took us a paper which was about 25 pages long in fine print to prove that. So that's what the mathematical proof is, really what the value of this result is. It's not like, it is quite intuitive. What I explained to you, I explained it to you in a very qualitative terms, so not much there to misunderstand. So you might be confused because you see it for the first time in your life, but if you've done that several times, you will know exactly what I'm talking about. So the achievement is that we were able to prove mathematically, rigorously, that all these methods, they will collapse onto the one. And that one will be equivalent to this joint eigenvector formalism. And that's all I wanted to tell you. So hopefully you took something out of these lectures. So maybe not everything algebraically, but at least qualitatively, hopefully you got the idea of what it is all about. And my punchline was that you have choices. All choices are good. Choices are up to you to make, and they will automatically work without contradiction with what has been known for 65 years. Okay, that's it. So I'm happy to stay. If you have any questions, I'm happy to stay, answer your questions for as long as they need be. So you still need to come here for the exam, right? So it is 2:30. 2:30, so don't stress out about it, but look through the notes, look through what I ask you to write on your own. So go through these, at least if not algebraical. So don't try to work too hard because your brain will be clogged. But qualitatively, look at the procedural steps. Make sure that you understand what they are. Make sure that you will be able to reproduce them. So If you get algebraic mistakes there, I don't care. So as long as what you do is logically correct, having like fresh mind, not after 3 hours of lectures, and having unlimited time, or at least sufficiently large amount of time, you will be able to pick up those algebra mistakes, so it's not a worry. But make sure that you understand the procedural steps, and really that's what I ask you to do, is just to show me that you understood them, or if not, well, I will take it as I did something wrong in my lectures. Next time, if I need to develop deliver such a course, I will do something differently. So it's essentially I would like to know what went well and what went not so well, so I can modify my teaching next time. Thank you.